All right, let's dive right into this explainer and demystify the incredible engineering that powers modern flight. You know, if you're anything like me, you absolutely love knowing exactly how things work under the hood. And honestly, when it comes to the sheer marvel of human engineering, very few things can even hold a candle to the complexity and raw power of aviation technology.
Just picture your last commercial flight for a second. You're sitting there in your window seat, cruising along at 30,000 feet, and right outside that thick pane of glass is an absolute monster of a machine just roaring away. It's massive, it's incredibly powerful, but what is actually happening inside that housing? I mean, how does a giant metal tube safely and efficiently push hundreds of people through the sky at near the speed of sound? Well, today, we're going to break the whole thing down.
To get started, think about the engine in your car, a reciprocating engine. It relies on a very strict sequence: intake, compression, combustion, and then exhaust. All of these stages happen one after the other, right inside the exact same combustion chamber. The chamber is basically occupied by one function at a time, but a gas turbine engine? Totally different beast. A huge feature here is that separate, dedicated sections are devoted exclusively to each one of those functions. And the craziest part? All of these functions are happening simultaneously and continuously, without any interruption whatsoever. It's literally a relentless, ongoing flow of energy.
So, here's our roadmap for today's explainer. 1. Anatomy of an engine. 2. The 4 engine types. 3. The turbofan takeover. And finally, 4. Understanding bypass ratios.
Starting off with Section 1, Anatomy of an engine, building the machine.
The typical gas turbine engine basically consists of these 7 core components, and they have to work perfectly in unison to sustain that continuous simultaneous operation we were just talking about. It all kicks off at the front with the air inlet, which channels air straight into the compressor section. This compressor violently squeezes the air, prepping it for the combustion section, where it gets mixed with fuel and ignited. That explosive energy then blasts through the turbine section, which, by the way, is what actually drives the compressor, before finally blasting out the exhaust section. And right alongside this main airflow path, we've got an accessory section plus essential auxiliary systems, handling all the behind-the-scenes stuff like starting, lubrication, fuel supply, anti-icing, and pressurization. Now, a really crucial point in industry lingo is how they split the engine into 2 completely distinct environments: the cold section up front and the hot section in the back. And it is exactly what it sounds like. The cold section refers to the parts from the air inlet right on through the compressors. But once you get past those compressors and step into the combustion chambers all the way through to the exhaust, you are officially in the hot section. It's just a simple, elegant way mechanics and engineers categorize the massive temperature shifts happening inside the machine.
All right, moving on to Section 2, the 4 engine types, a visual guide. Here we have the 4 primary types of gas turbine engines used to propel aircraft today. You can really see how that internal anatomy we just covered translates into 4 distinct forms. Up at the top, there's the turbofan, which you can easily spot by its massive front fan. Below that is the turboprop, where the turbine's energy actually turns a gearbox and a traditional propeller. Then we've got the classic turbojet, which is this sleek, straight-through design where all the energy exits strictly as exhaust thrust. And finally, the turboshaft, typically used in helicopters, where the engine's power spins a dedicated power shaft instead of just blasting out thrust. Each one is tailored for a very specific job up there in the sky.
Let's hit Section 3, the turbofan takeover, the undisputed king.
Look up at the sky today, and you really have to ask yourself, why do almost all modern airliners specifically use the turbofan engine? Like, what makes it the undisputed king of commercial travel? Well, check out this staggering fact. A massive 80% of a turbofan engine's total thrust is produced just by that giant fan at the front. not the fiery core exhaust that you'd probably expect. Don't get me wrong, the engine core is absolutely necessary to keep the whole operation spinning, but the vast majority of the actual pushing power, that comes from that massive set of fan blades acting almost like an incredibly advanced ducted propeller. To really understand why this is such a game changer, we have to look at the other options on the table. When we compare the pure turbojet to the turboprop, a pretty clear problem emerges. The pure turbojet is fantastic for high speed. We're talking those 0.8 Mach speeds that airliners fly at, and it absolutely thrives at high altitudes. But it has major problems with deafening noise, sorry to anyone living near an airport, and it guzzles a massive amount of fuel. On the completely other end of the spectrum, you have the turboprop. Highly efficient, produces high thrust right off the bat, which lets aircraft use way shorter runways. But its fatal flaw for modern airliners? Turboprops are generally only efficient in that 300 to 400 mile/hour speed range. They just cannot keep up with the jet-setting pace we demand today. So the takeaway here is that the turbofan acts as the ultimate compromise. It was purposefully developed to perfectly balance the high-speed, high-altitude capability of a turbojet with the stellar operating efficiency and high thrust of a turboprop. By turning that large set of fans at the front, the turbofan engine runs quieter and gets vastly better fuel consumption in that high sub-max speed range that all of modern commercial aviation relies on.
Which brings us to our final segment, Section 4, Understanding Bypass Ratios, the secret to efficiency.
If you follow the airflow here, you'll notice something absolutely amazing. The air being driven by that massive front fan. A huge chunk of it does not even pass through the internal working core of the engine. It completely bypasses it. The core itself, often called the gas generator because it houses the high-pressure compressor, the combustion section, and the high-pressure turbines, is working away right in the center. But surrounding all of that is this secondary stream of cooler air. Plus, many of these engines use a two-spool design. That just means there are two independent concentric shafts spinning inside each other, a high-pressure spool making up the core and a low-pressure spool containing the fan and the turbines needed to drive it. And that brings us to a really fundamental concept, the bypass ratio. Simply put, this is just the amount of airflow, measured in pounds per second, bypassing the core compared to the amount of air flowing directly through the core. Most transport category aircraft today use high bypass engines. Why? Because the general principle is to convert more of the fuel's energy into pressure rather than just relying on raw exhaust speed. By pushing a massive volume of bypassed air, you gain a huge advantage in additional thrust without actually increasing your fuel flow. The end result? Superior fuel economy and a massive boost in the aircraft's range. The fan is doing most of the heavy lifting, completely making up for the decrease in thrust coming from the engine's core.
It really goes to show how aviation is quite literally a masterclass in compromise and continuous refinement. So the next time you look out that window on a flight, you won't just see a noisy metal tube. You're going to picture the cold section and the hot section. You'll envision that cooler air effortlessly bypassing the roaring core, and hopefully you'll appreciate the masterful engineering of the gas turbine pushing you safely through the sky. Keep wondering, keep learning, and I'll catch you on the next explainer.